So an interesting help desk question came in recently, and I thought it would be kind of good to try to explain it a little bit more. A user was looking at a spectrum, and they were plotting one of the model components, a Gaussian, and they noticed that the Gaussian had multiple peaks, and they were trying to understand, or they wanted to know why would a Gaussian have multiple peaks. Um, the answer is simple. It's just that they're actually looking at the effect of the response matrix, the RMF file. But I thought it'd be kind of good to go through an example of this to kind of show you how to visualize this and just take a look at it. I'll try to get the notebook here uploaded on this blog. And yeah, so we're going to start. We're going to load Sherpa, load matplotlib. I'm ignoring some warnings here, don't worry about that. I've got a random data set here, just a random spectrum that I've extracted somewhere. I don't even really remember where it was from. But you'll notice that when Sherpa loads the data, it automatically loads the RMF and the ARF. And the important thing here too is that not only are they loaded, but they're actually added to the model expression. So now I can go through and just, I don't really care what the data looks like. I'm just going to play with the source model itself. So I'm going to set the source to be a Gaussian 1D. And I'm going to set the position to be 6.5 keV. It's the iron line. Whole width half max of 0.1 keV. It doesn't really matter what it is. And then I'm going to plot up the data. And indeed, my simple Gaussian has 4 peaks in it and all kinds of other structure, and there's a knee here, and there's a kind of reverse knee going in that direction, and a long tail going in that direction, and obviously Sherpa must be broken. It's not. This is just the actual RMF. This is the line spread function for the people from the optical world. So an incident energy at 6.5 keV may be detected at all of the pulsites, at all these pulsites. Now this is a probability curve, so there's a normalization difference here, but so you can see, there's the very low probability that this will occur, but it's not zero, and it's calibrated. So we can kind of see this if we actually look at the actual model expression itself. So if we show model, we can see we've applied an RMF, we've applied an ARF to our Gaussian. This is the normalization, this is the exposure time that gets added, again, automatically by Sherpa. And now let's say, okay, fine, that's great. Sherpa's a wonderful thing, it's doing all that stuff, but I just want to make sure the Gaussian's where the Gaussian's supposed to be. So instead of plotting model, I can plot source. And source just shows the source model without being involved through the RMF itself. So Sherpa's fine, the detectors are fine, everything's good. Kind of the one thing I want to show though is that ultimately the RMF is a matrix. It's a 2D image. It's a 2D array, and 2D arrays are images. Though it's actually stored physically on disk in a weird table. It's a Fitz-ism. It's a binary table that has variable length array columns, which basically just means it's really hard to read. And unless you're writing software specifically to read this format, it's a pain. But we can actually convert this obscure format from a table into an actual 2D image using one of the child tools, RMFImage. And basically it's just RMFImage the RMF that comes in, the image comes out, and we'll delete any files that exist on disk. And if we take a look at it, we can see that it's now an image. And not only is it an image, but it actually has coordinates attached to it actually has world coordinates attached to it. So we know that the x-axis is pi, which is pulsite channel, and the y-axis is energy, which is in kV. We have an image, so let's fire up DS9. And there's DS9. We can bring it up, and this is what a RMF looks like. We can see it's not. It's largely diagonal-ish. It's not, it's not diagonal perfectly, but there's also all this. You can kind of see here if I play with the scales. There's all this low-level structure that's in here. One of the easiest ways to visualize this is we just come up here and say View Horizontal Graph. Okay, so we can see it's there, but graph parameters. I'll make this log scale, and we see the same thing we saw before. Now it knows about it, so I'm going to actually do this just so I can crosshairs. Come up here. We can see the PI energy, so it knows X is PI, Y is energy. So I can move the crosshairs up to, about 6.5. Oops, too far. But you can see this basically now looks like the same structure we saw up here. It's a little different because this is actually convolved with the Gaussian that does have some width, whereas this is the raw value. But it's just another way to visualize the RMF identity energy. For anybody who's kind of curious, so this is the main probability that there's almost a linear relationship, which is expected. This is caused by the silicon fluorescing. So this is the silicon fluorescence peak, and this is the escape peak. So this is basically mathematically, it's basically this energy minus this gives you that, or yeah, it's this much energy offset from there as a constant. The other kind of structures that are here, they're actually things that are affected by the event detection process. So this knee here is actually caused by the what we call the grade selection and the way the thresholds are applied. That actually introduces this this knee or this discontinuity or this slope here. And there's other good physics things happening down here at the low end as well. But so this is a typical ACIS RMF. You'll see different RMFs for every place on ACIS. The front side and back sides are different, so yours may look slightly different than this. That's kind of about it.